Okay, so I believe we should start today's session. All right. So, so this is, I believe, I am audible. Someone can respond. Hello.
Yes, audible.
Yes, thank you. All right. So, as you all know, the course is Fundamentals of Compressible Flow, being conducted by NPTEL. All right. So, this is the fourth live tutorial session. We already have been through three such sessions. So the instructor of this course is Professor Niranjan Sahu, all right, affiliated to IIT Guwahati, Department of Mechanical Engineering. And my name is Aditya Sharma, and I'll be the teaching assistant for these live tutorial sessions. I have been for the last three, and this is our fourth such live tutorial session. I also am affiliated to IIT Guwahati, all right, Department of Mechanical Engineering, pursuing my PhD under Professor Niranjan Sahu. All right. So today we will be dealing with the normal shocks. All right. So this is, I believe, the fourth, right? Fourth session. This is our fourth session. For you guys also, this is the fourth year, sorry, week. All right. So we shall try to see some problems based on what we have learned in the from the lectures of week 4. All right. So previously what we have done and what we like how we proceed in these sessions is how we have evolved this. Few of you already know. So I would just repeat that we would just in the starting we would just go through the topics that have been covered in the respective week lectures, and then we then move on to the questions related to those topics. And from the last session only we are uh, doing questions based on topics. So we are trying to do topic specific questions. So these topics questions have been asked from these topics in your assignment also. So this would this should cater to like our needs vis-a-vis solving those problems, all right, assignment problems. So we shall proceed then for today's session, all right. Okay, so let's see the topics. So in this lecture 10 video, so we first heading was first main heading was introduction to shock waves. So a brief introduction to shock waves was given here, and then these events, subsonic and supersonic events, were discussed, like various features related to these events were discussed, all right. And then briefly there was these characteristics of supersonic events. So like irreversibility, like in real scenario what happens when we encounter a shock wave that uh, has been discussed in these lectures, all right. So this topic was just a brief introduction to shock waves. Okay. Then there was another heading by the name formation of shock waves in one-dimensional medium. So as the module also suggests, we are trying to model the normal shock waves, all right, for the sake of our study, all right. for the sake of our study, we are trying to model a normal shock wave, and for that only, all right, in that quest only, we have this formation of we have like gone through this particular topic. Okay, sorry, we've gone through this particular topic. So this formation of shock waves in one-dimensional medium. In the last week, we just saw this one-dimensional case of the compressible flows, all right, quasi 1D flows we discussed in the last week lectures. All right, so here also, though we are not here, we will not be dealing with the quasi 1D flows, but just 1D flows. There won't be any change in the area as there is movement of flow in a particular tube. All right. So then there was subtopic related to this was development of compression waves. So we like in the lectures we saw, so there was a, by means of a this piston example, this compression wave has been explained. All right. So like if in starting there is a piston moving with constant velocity, so this way it has been initiated, and then uh, if we move the piston from rest to some velocity, so obviously there will be like a gradual change in the velocity, so it won't be a constant velocity. So in that case, like if there are different compression waves taking place for a particular fluid, so how do these compression waves interact with each other? So this has been discussed. All right, then as I said, how they interact. So next subheading is the merger of compression waves. So this has been discussed, like how these compression waves merge, because it is seen that if like there is one compression wave moving in one direction and we increase the piston's velocity, so the next compression waves velocity would be greater than the velocity of previous compression wave. So obviously, as the relative velocity of this compression wave is larger than the previous ones, so this they will like collides at some point. All right. So they will meet at some point. All right. So this has been discussed in this topic, and then we came to this normal shock scenario. So this has been discussed, like how the merger in a limiting case of like if there is this instantaneous merger of these compression waves, so then we get a normal shock. All right. So this was in this heading, this was discussed. Then we came across moving normal shock and stationary normal shock. So like in wind tunnels, I have already like mentioned it in one of the previous sessions. Like I have briefly discussed it, like shock waves can be stationary and shock waves can be moving. So if we want to simulate a moving normal shock, then one good example is shock tubes. All right. So for this case, shock tubes. I personally work on shock tubes. Okay. So this is the case of moving normal shock. All right. Then there is stationary normal shock also. All right. Like in wind tunnels, if we want to capture a stationary normal shock, so in wind tunnels we can have this. we can have these. Stationary normal shocks. If we want to simulate such shocks in in our laboratory environment for the study purposes. All right. Then in real scenario also, the moving shocks are quite common. Like if there is a blast, okay, so that shock is obviously a moving shock. All right. Then we went on to learn these fundamental equations for normal shock. So fundamental equations. So across the whole study of fluid dynamics, you will come across these fundamental equations. All right, be it incompressible flow, be it compressible flow. Okay, so you will frequently like counter these equations. All right, so which is nothing but continuity equation. Wait, I'll write somewhere else. Continuity equation. Right. Oh, sorry. Then there is momentum equation. Then there is energy equation. And one more topic was discussed that I'm missing. Right. Yeah, thermodynamic relations. So these things were discussed in this fundamental equations of normal shock topic. Right? So continuity equation is nothing but rho 1 u1 equals to rho 2 u2. In the same way, there is momentum equation. All right, p1 plus rho 1 u1 square equals to p2 plus rho 2 u2 square. All right. Then there is energy equation, that is h1 plus u1 square by 2 plus q. I believe you must be knowing these. All right. Let me just write these here. Okay. So continuity equation is rho 1 u1 equals to rho 2 u2. All right. Then momentum equation is P1 plus rho 1 U1 square equals to P2 plus rho 2 U2 square. All right. Then there is energy equation, that is H1 plus U1 square by 2 plus Q equals to H2 plus U2 square by 2. Okay. So these are the fundamental equations that have been discussed in this particular topic. All right. Then there are assumptions related to such a discussion. To what extent these equations hold true or good. All right. Assumptions is a very important part of any theoretical analysis. Okay, so that cannot be taken lightly. Okay. All right. Then moving on to our next lecture. All right. If somebody wants to add something in this lecture, 10 topics, he or she may, or else I shall move to this next lecture, topics of next lecture. All right then. Okay. All right, then there was lecture 11. So there are total 2 lectures are there in this fourth week's content. Okay, so lecture 11. So first topic in lecture 11 is normal shock analysis. So here we are trying to analyze normal shocks. So different properties, what are the changes in those properties of a flow that are encountered when there is a normal shock, when the flow comes across with a normal shock. So this has been like introduced in this topic, and then this is revision of the previous lecture. The first this section is basically the revision of the previous lecture. So the assumptions and fundamental equations that were discussed in the last topic of the previous lecture. Okay, so then there was this topic, Prandtl relation for normal shock. All right, which is this relation. All right, m2 star equals to 1 by m1 star. So this has been introduced in this topic. Okay. All right. So then few one or two relations based on this have been given in that particular slide. All right. Then we moved on to this. Okay. Then there was this fundamental equations. All right. Okay. So major thrust of this week's content is this particular section. All right, though the content that has been discussed till now is obviously very important from the point of view that we must know the basics of normal shock, all right, and some behaviors related to a normal shock. But then this section, the flow property calculation across a normal shock, it's very, I must say, of utmost importance as far as a normal shock is concerned. All right, a normal shock wave is concerned. Okay. So, and we shall come across various questions based on this particular section also in this upcoming part of this particular session. So different topics that have been discussed. All right. So first one is this Mach number relation. So across a normal shock. All right. So this relation. All right. Just writing these so that because we have to use these later. All right. So this is the, so here M2 is the Mach. So this is after and this is before. All right. So any type of normal shock, by any type I mean be it moving or be it stationary. All right. So in any of these scenarios, so if M1 is Mach of the flow already before this shock, then after this normal shock, let's say M2 is the Mach of this flow. All right. So how do we relate these two max? So that can be done using this relation that I've just written. All right. Okay. So then there is static density and speed ratio. All right. Similarly, this density and speed ratio is there, which is rho 2 by rho 1 equals to u1 by u2. So this has like from this particular equation has also been given in your current assignment. All right. So this you should take care of this particular relation. Okay. And then there is a static pressure ratio. Okay. So this is our static pressure ratio relation. P2 by P1 equals to 2 gamma by gamma plus 1 m1 square minus 1. Right. This is the static pressure relation. Then there is static pressure ratio. Right. Then there is static temperature and static enthalpy ratio. Okay. So this enthalpy and temperature ratio, right? T2 by T1 because H is CPT, right? So it can be written like this. Where M star equals to gamma plus 1 M square by 2 plus gamma minus 1 M square. Alright. So this is H2 by H1, alright. And static enthalpy ratio. I'm writing all these relations so that when we do our question, so these relations are in our hands, all right, so that we can use these relations. Then this is stagnation conditions. All right. Okay, so stagnation conditions has been discussed. Then what is the next topic? Okay, then the next topic is Rayleigh-Pitot tube equation. So then there are another set of relations related to this. All right. So for this Rayleigh-Pitot tube equation, oh, okay, this is so something like this is there. So then this is there. Then after that we have entropy change across a normal shock. All right. So I'll just quickly write this relation also. It's taking a lot of time. P2 by T1 minus R ln P2 by T1. All right. And one another such relation is there, which is S2 minus S1 divided by R. So these are our relations. All right. So these are our relation with respect to this entropy change across a normal shock. Okay, so this is the discussion as far as the topics of these lecture 10 and 11 are concerned. Now we shall move to the questions. All right. So up till this point, if somebody wants to add something, he or she may, or if you want to like ask something, then you can also do that. Yes. So no questions. Shall we proceed then further?
Yes.
Okay. All right. So this is fine with Yogesh and Harshit also. Okay. No reply. Then we shall proceed further with our questions. All right. So this is the first question. The topic is flow property calculation across a normal shock. So this is related to Mach number across a normal shock. Okay. So the question is Mach number across a normal shock is a function of dash and dash. Okay. Or this should have been like this. Either one can be true or two can be true. So yes, answers from your side. Answer. All right. So I have just I have written this relation. All right. So this is our relation for this particular relation. M2 square equals to 1 plus gamma minus 1 and so on. So here there are two things. This is one is gamma and then one is M1. All right. So if you see the question, this Mach number before a normal shock. So this is M1. Okay. And then there is no specific uh, volume in this particular relation, and specific heat ratio is there. All right. Yes. So the D option will be there for this particular question. Okay. All right. Yes. No answer.
Yes.
Yes. Yes. Okay. All right. All right then. Okay. So then we have this second question. So the topic is flow property calculation. So again, as I've already told, so this last section of this is very uh, essential as far as this particular week is concerned. All right. So flow for this. So this question is next question is for flow properties across a normal shock. Which observation is false? All right. So let's see the options. Okay. So we have four options here. First option is the velocity decreases. The second option is total pressure decreases. Then next is static pressure decreases. And then there is static temperature increases. So for flow properties across a normal shock, what is false? So as we know, so across a normal shock, so obviously the velocity decreases as the flow moves across a normal shock. But then what happens to total pressure? Does it decrease or increase? So in any case, the pressure is not going to increase. All right, total pressure is not going to increase, but we see that there are pressure losses as a flow moves across a normal shock. All right, so the second option is also correct. Then the third option is static pressure decreases. All right, so this option is a little bit dicey. So does this happen across a normal shock or not? Static pressure. Does it increase across a normal shock or decrease across a normal shock?
Increases.
Yes. So I believe we have this relation also. Static pressure ratio relation also we have there, all right. So this relation, because this relation says mathematically, if we see, all right, if we mathematically see, this is this relation. And because, so this is this relation. So because this is a normal shock, all right. So m will be greater than 1. All right. We already have 1. All right. So adding something to 1 will be greater than 1. So this clearly shows that P2 will be greater than 1. So if we somehow remember the mathematical relation, so from there also we can deduce this, that static pressure across a normal shock increases and it does not decrease. All right. So static temperature increases. So this also is true. So across a normal shock, we see that this temperature, static temperature increases, certainly increases. All right. Then so if this is clear, let's move on to next question. If you have some doubt, then let me know. Otherwise, we shall move to our next question. No. No questions? Okay, then let's move on to our next question. All right. So next question is based on this topic, characteristics of supersonic events. Okay. So characteristics of supersonic events is a topic from lecture 10. Okay. So this question is from there only. And this has been asked from this topic, question has been asked in your assignment also. So the question is entropy across a normal shock dash. Yes. What happens to entropy across a normal shock? Can we directly pass some comment on entropy when we are dealing with normal shocks, or we cannot say anything? Okay.
Increases.
Increases. All right. Okay. So let's see. Increases. Yes. Yes. So we have the last topic, last two subheadings we have. All right. On entropy change. So if we do some numericals based on that, we can easily figure out that there is entropy increase in the flow across a normal shock. All right. So obviously there is there is also internal energy increase in flow across a normal shock. Then there is also static temperature increase in flow across a normal shock, and eventually which leads to an increase in entropy across a normal shock. All right. So we can surely say that there is this entropy increases when we move across a normal shock. All right. Okay. So this is this was our question number 3. Okay. So A is the answer. All right. So let's see the next question. Flow property. Calculation across a normal shock. So this question is a density across a normal shock. So what happens to density across a normal shock? I have to answer this. Yes, I saw Harshit replies on chat. So that's fine. Yes. All right. So for density, he says it increases. All right. So what does Ginny say?
Increases.
Increases. All right. So these are like basic things that must be kept in mind. So as students of compressible flow, we cannot miss these things wherever we go. So these we should not fumble on these basic questions. Yes, you are right that density increases across a normal shock. All right. So across a normal shock, what happens? So if I draw this, E1, rho 1, E1, right? P2, rho 2, T2. Then there is, in total terms, there's T not 2 also and P not 2 also. Oh, sorry, should have written P not 1, T not 1, and there is T not 2 and P not 2. All right. So across a normal shock, what happens? P2 is greater than P1. Yeah. Then rho 2 is greater than rho 1. All right. Then what is there? T2 is greater than T1, right? But then there is one also very important property or parameter, that is velocity. What happens to velocity? Let's write U2 here. What happens to velocity? Velocity decreases, right? Also Mach decreases. M2 is less than M1. So these are basic trends of different properties and parameters that we have to keep in mind and we should keep in mind. All right. So basically, these are basically very fundamental questions, but at the same time very important. So we should keep these in mind. All right. So let's move on to next question. So this is a numerical type question. Just have a look at this question and then we shall try to solve this. Just have a look at this question. Okay, so we will try to solve this particular question, and I definitely want help from you, answers from you. Okay, so let's move on to our this question. Topic is flow property calculation across a normal shock. So the same topic, all right, but some other subdivision of the same topic. Flow property calculation across a normal shock. So a flow with Mach 3 experiences a normal shock. So calculate the, yes. So somebody, Harshit has calculated M2. All right, we shall see. We shall see. Okay. So calculate the Mach across the normal shock. Assume the specific heat to be 1.4. So let's do this. All right. And then we shall see the answer to this question. As this is a tutorial session, so I cannot just plainly take answers from you guys. So I'll have to solve this in any case. All right. So let's see. Harshit has given one. Let me know if I make some mistake while solving. All right. By mistake, if I write a wrong expression. Okay. So this is the expression for Mach across a normal shock. Okay. Okay. What is gamma? Gamma here is 1.4. What is M here? M1 is 3 square. All right. then divided by 1.4 into 3 square minus gamma minus 1. Gamma is 1.4 minus 1 divided by 2. So this becomes 0.4 divided by 2 into 9, right? 1.4 into 9 minus 0.4 divided by 2. One plus 1.8. This is 12.6 minus 0.2 divided by 12.4. Yes. So I'm getting this. Harshit is also getting this. And what is Ginny getting? No answer from Ginny's side. So I believe this is the correct answer. All right. Okay. So when I calculated, I didn't take the under root of this m2 square. All right. Then I made a mistake here. So it should have been 0.47 between. So yes, the answer should have been this. Right. Okay. So let's move on to the next question. Shall we? No response. All right.
Yes.
Okay. Thank you. Thank you. So let's see the next question. So this is from this assumptions part of the fundamental equations for normal shock. So as I have already mentioned, the assumptions part is very important when we are dealing with the theoretical part of normal shocks, or in such scenario any. Okay, yes, we have answer from Harshit. So what I was telling is that from the uh, this any like topic we are theoretical topic we are discussing, in that case assumptions are very important, because uh, the solution we get from that discussion holds true for those assumptions only, as far as those assumptions are true. So in that scenario we are good to use this particular theory related to that topic. In another case we cannot just like plainly use uh, such theory. All right, so we should have to tweak it in some manner to get to our correct understanding of that particular topic or scenario, real time scenario. All right. So a normal shock wave is dashed to the streamlines. So here we have four options. All right. That this is not the case for all types of shock waves, but yes, certainly for normal shock waves, it has a relation to streamlines. All right. So we have answer from Harshit. Harshit says that it will be perpendicular. Okay. So the concept of streamline, I believe you guys must have gone through in your basic fluid dynamics or mechanics course, right? So in a streamline, at any point, if you draw a tangent, you get the direction of velocity of fluid flow, all right, at that particular point. So all such points when we take together, so we get a streamline, and there are properties related to streamlines. One such property is that two streamlines cannot cross, because at a common point then there will be this dispute that what should be the direction of the velocity. So in that case it won't, the definition of streamlines won't hold true. So this is one such property of streamlines. Okay, so such streamlines have been mentioned in this question. So if this is the streamline, so what would be the direction of the normal shock wave? Would it be in this particular direction only? This is the normal shock. Would it be at some angle? Certainly there are some shock waves that are at angle, all right. But then for this case, Whether this is true or not, we should see that. Not like this. The normal shock like this. Or like this. Just trying to draw there. This is our A option, this is our B option, this is our parallel, this is our B option. Okay. Harshit says this is the right answer. So Harshit is correct. All right. So when we analyze the normal shocks based on our assumptions, so we do take normal shocks to be perpendicular to the streamlines. In our analysis of the normal shocks, we take stream tubes. What are the stream tubes? Stream tubes comprise of set of streamlines. Okay, so when we are doing the analysis of a normal shock, we keep ourselves confined to that particular stream tube only. All right. So it's all these concepts have been introduced just to proceed for the mathematics of the physics of these like phenomena or phenomenon. All right. So a normal shock wave is perpendicular to the streamlines. So this is the right answer to this question. All right. Okay. So 1 hour has passed. All right. So as we are doing in the past sessions, in this particular session also, we should take a 5 minutes break. All right. And then we should proceed further for this session. Is it fine with everybody? Yes.
Yes.
All right. All right, Harshit. Uh, yes. Okay. Thank you. All right. So we shall take a 5 minutes break and then we shall proceed further for with our like set of questions, remaining set of questions for this session. Okay. Okay, so let's continue with the session. All right. If you guys have joined, so we can proceed further.
Yes.
Okay, okay. So just go through these four lines and let me know which one is not an assumption for the fundamental equations of normal shock. First option is based on frictional effects. Second is based on the shock tube, this shock wave's thickness. Then whether the flow is adiabatic or non-adiabatic. Then there is this steadiness or unsteadiness. Yes.
Option D.
Option D. Okay. Ginny has replied option D. Harshit has also given this in the text chat. All right. So these these assumptions must be taken into consideration. All right. While we are dealing with these fundamental equations. Okay. So yes, so this frictional effects are negligible. So when we are trying to study this normal shocks, so theoretically, so we make some assumptions, and this frictional effects in that case we neglect. All right, so we don't want to consider the frictional effects or the heat related to the heat generated related to the because of the friction. So we don't want to increase the complexity of our flow physics by including those elements also. Otherwise it will become very hard to handle the mathematics of the flow physics. All right, then the shock thickness, also we consider that the thickness of shock is very small in comparison to the stream tube we are uh, supposing in our this analysis. All right, so because it's in our hand to, when we are analyzing, it's in our hand to choose a stream tube of particular size. So in that case it is very important to consider the thickness of the, to keep the thickness of the shock in sorry, in such a way that it's it's very small in comparison to the stream tube. So in your lectures content also, you must have gone through the, like, the thickness of the, what is the order of the thickness of the these shock waves, right? So then the third option is the flow processes including the shock wave can be considered to be adiabatic. So this is obvious that we don't want to consider the heat effects. All right, so we avoided this friction also because of that. It was one of the reasons, all right, to not consider the frictional effects. Then here it's straightforward that we don't want to deal with the energy perspective of the shock waves in this manner, that we are including some heat to the this flow, and then we are studying the flow physics. So we don't want to do that in the initial phases, when we are just trying to make sense out of the normal shocks. All right. Then the flow across the shock wave is considered to be unsteady. So the flow in the assumptions, the flow across the shock wave is considered to be not unsteady but steady. All right, because unsteadiness is also a very big headache, I would say, when you want to like solve a flow physics problem. All right, so option D is correct. All right, you guys are right. Okay. So check this question now. Okay. Yes, Harshit has given the answer. What does Ginny say? Which option?
The book, D.
D. You're also saying D. Yes, so this is like very straightforward from the formulae only of this entropy change, all right? So this is what is, it's like, so I've already written it. I'll just, oh sorry, I'll just do a recap. All right. So two expressions I had written. So this is Cp ln P2 by P1 minus, sorry, T2 by T1. T1 minus R ln P2 by P1. And then this is P02 by P01 equals to S2 minus S1 divided by R. So static pressure ratio. So here we have our static pressure ratio. Sorry. Here we have our total pressure ratio. And here we have our specific heat at constant pressure. Right. So D option is correct. Right. Okay. So let's move on to our next question. So in your this assignment, you have one question related to, so this is this, one question related to this topic. Yes. Yeah, this one topic related to this, and question, a numerical question related to entropy change, question number 9. All right. So here, as I have mentioned in the previous session also, I cannot solve the assignment questions. All right. but then some idea we can get based on the topics that are involved in that particular question. And in any case you are facing some problem, you can just ask me. All right, and I'll try to give some explanation related to that. All right, that might be helpful to you guys. All right, so this is question number 9. Entropy change as a function of stagnation pressure. So this is the previous question only, the topic like topic wise. So it's the same topic as it was in the previous question, but here we have a numerical. So let's see the numerical. So initial and final stagnation pressures across a normal shock are given as 5 bar and 3 bar respectively. Find a specific entropy change across the shock wave if the universal gas constant is this. Yes, solve this. Solve this and give me the answer. This is question number 9. Here we are provided with P01, that is 5 bar. We have been provided with P02, that is 3 bar. Right? Then we have been asked to find this. Right? It's just a straightforward question. But would essentially do the revision of and this hands-on practice of this particular formula. So what is S2 minus S1? Now you guys should be able to solve this, right? Universal gas constant has been given as 287 and P2 is 3 and P02 is 3 and P01 is 5. So please solve this and give me the answer.
146.6.
46.6. Arshid is also getting 146.6. Okay. I'm also getting 146.6. Okay. So this was it for question number 9. So this is our range and our answer falls in this range only, 146.6, 46.61 joule per kg Kelvin. Okay. So we are good up to this point, right? Then Yes. Okay. All right. So moving on to our next question. Now see this question. And let me know how you solve this particular question. Is there any idea?
Continuity equation.
Sorry. Yes. Continuity equation, Ashish is saying. If I have heard it right. Am I right, Harshit?
Ah,
Okay. So let's first of all read this question and then see how to proceed with this. All right. Right. So we have been given this static pressure, static density, and velocity, right? Before a normal shock. So P1 is given as 2 bar. All right. Then, okay, let's write it here. One is given as 2 bar, which is nothing but this. All right. And then rho 1 is given as, how much is rho 1? Rho 1 is 3 and U1 is 400 kg per meter cube. U1 is 400 meter per second. Okay. P2 is given as 3 bar. Okay. .8 kg per meter square. Okay. And then this has been asked, right? Right. So Harshit says that it can be done by, okay. Right, so when I was just framing this question, So it did not click my mind. I did it using momentum equation, but let's see how these differ. All right. Then because continuity equation, it should follow, the question should follow the continuity equation also. Then this question won't be a correct question. All right. And then let's see. Rho 1 u1 equals to rho 2 u2. Three into u1 is rho 2 3.8. Comes out to be 50. All right. Let me just calculate it. Into 400. 315.78. Though this falls like it would fall in this range, but then it will fall in that range. But then, like if you try to solve it using this momentum equation, right? Because it should have the same. If you solve it using this, right? P1 plus rho 1 u1 square. P2 plus rho 2 u2 square. Plus I'm just cross checking, right? Because the answers from the both should not vary. Like if you're while framing question, this should have been considered. But if it's not considered, then it's not a right question. Right? This is it. So from this we get minus 10 raised to power 5, right? And then from this we get 48 and 4 zeros. Okay. So this is, sorry. Nothing but 4.8 into 10 raised to 5 minus 10 raised to 5. 8 square, right? Is 3.8 into 10 raised to 5 equals to 3.8 u2 square. So if you just solve this, so it comes out to be this, right? So I believe these differences should not be there. So while giving pressure values, this should be taken into, should be considered, all right? But then while framing, I didn't consider it. Although the answer falls in this range, but then I believe it's not the correct way. Anyways, okay. So yes, so this was it. But then I have some more questions. All right. So, oh yeah, okay. Because we have time, all right. So we shall see some more questions for this session, and then we shall conclude today's session. But we have time, so we'll just try to go slow because we are left with at present around 27 minutes. Okay. So this is mathematically a normal shock is represented as a dash in a medium. Okay. So as per the options, you have to answer. Yes, what is the answer to this question?
Discontinuity.
Discontinuity. B. Okay. So Harshit also says discontinuity. So why do we need to like consider this as a discontinuity if this is the correct answer? But before that, we shall just see all other options. Okay. So first option is so discontinuity in the sense like if we are like drawing some pressure graph, all right, with respect to let's say some distance. Okay. So what happens to that this pressure in this flow direction, all right? So how do we represent a normal shock? Okay, whether the trend will be like if here the normal shock is so whether the so if this is a normal shock, so whether the trend will be like this, all right? I believe you all understand what the discontinuity is, right? In this mathematics, we study this. In this calculus topic, we study this, right? Arshad?
Step function.
Okay, yes. Wait. Yes, I'm just like discussing this uh, a continuity concept, like from where it has been first introduced to us, all right? So I'm just discussing this, and then what you're saying, I'll just like touch upon that point, all right? So if you see like in calculus we have studied this whether the function should be continuous or whether the function should be uh, how the function is continuous and how the function is discontinuous, all right? And then we later in mathematics studied the differentiation. All right. So whether the continuity has something to do with the differentiation or not. All right. So that we have studied in mathematics, and there it has been like we learned from there only that so a function for a function to be differentiable, it should be continuous, right? So if the function is not continuous, so it won't be differentiable at that particular point, right? So like there is modulus function, right? So modulus function is or is a modulus something like this is a modulus function, right? If this is y and this is x-axis, right? Just draw it properly for you. Because I was discussing continuity or discontinuity, right? And then let's say this is x-axis and this is y-axis. So this is our modulus function, right? Y equals to f of x equals to x this. So whatever you put in this modulus function, the graph will be like this. But then at this point, though the function is uh, continuous, but then there is this like the graph is not smooth. All right, so in that case we cannot differentiate this function at this point. So in that sense only, so this discontinuity is there in this particular topic. All right, so this is I was mentioning that. So if this is this normal shock, right? So whether the function will be like this, will it be smooth, or like I have written this, whether the function will be like a modulus function, or whether it will be discontinuous. All right. So in your this lectures also it has been discussed that. So for this has been discussed for this compression waves, right? For compression waves, how the pressure is, right? And then it was further discussed that if this is one compression wave, all right, this is another compression wave, and this, let's say this is first and this is second compression wave. So if the first compression waves moves ahead of the second compression wave, so if second compression wave has been generated by increasing the velocity of the piston, so by means of this piston example, this has been discussed. So if this velocity of the piston has been incremented with respect to the first this velocity, in that case the how the this pressure variation will be with respect to the distance, all right, in the this in this particular cylinder in which this piston is, and the where is pressure. So this is for, let me write compression wave as 1, all right, and this as compression wave 2, all right. So in this case what will happen is, so this is the level of compression wave 1, all right, and this is the level of compression wave 2. So for the compression wave 2 and the compression wave 1, so how they will differ and their pressures will, how their pressures will differ is defined using this particular discontinuity, all right. So like Harshit, like just like quickly mentioned, so this he said step function, all right. So in our analysis, so if we have to define this shock wave in terms of pressure and mathematically, if we want to define it, so we do it with a this step function or with this type of discontinuity, because this pressure jump is very abrupt, all right. So in this lectures also this has been mentioned, this has been discussed that, so this is a this limiting case, all right, limiting case of merger of compression waves, all right, in which the time tends to zero, all right. So if the time is tending to zero, obviously it's a limiting case, all right. So limits we then again limits we have studied in this uh, continuity and calculus, all right. So for the modulus also, like I was saying, this there is peak, so at that point the limit is not defined. In that sense we define that this point is discontinuous, all right. So this concept of limit, okay. So we here I mentioned a limit in this time sense, the merger of compression waves in some time, all right. So we when mathematically we are dealing with the normal shocks, so we take this merger of this different compression waves when we are modeling this normal shock. So we take this merger of compression waves as happening in a very small time, all right. We take this limiting case where t is tending to zero, all right. So, and how do we represent that on graph? So we represent that on graph using this step function, all right. So this is our step function, okay. Then we have this next question. So this is the discussion related to this discontinuity of this normal shock, all right. So if we move on to next question. So typically the thickness of a shock wave is of the order of, yes, it's a
10
factual
pound
question. Yes, 10, yes,
C.
C, okay. Genie says C. And what does Harshit say if he's still with us? Okay, Harshit also says C. Okay, so you can like imagine and wonder like how thin a shock wave is, all right. So it's to the power of 7. You both are correct, right? The option C is correct. But one should like wonder, like we are studying shock waves, and how thin a shock wave. Some like reality sense we should like have like how some visualization of the physics we should have as a fluid dynamicists, right? So it's less than even micro, right? So in because of that this particular region only, so there are drastic this flow property changes, and how do they affect further the objects that are linked to these shock waves, all right. So when we see the aerodynamics of like supersonic vehicles objects, so in that case how these flow properties come into picture, all right. So that needs to be wondered, right? So this is question number 12. All right. So option C is correct. Then let's move on to next question. Right. Yes. Shockwave is a mechanism of instantaneous dash of a gas within a thin region.
Compression. Compression.
Okay. 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 Yes. Ginny says compression. Sharshit also says compression. Yes. Yes. All right. All right.
Question I have one. It will be
You have
doubt.
a yeah. Yes, Harshit.
So let's say some person physically encounters with the shock wave. So
Okay.
the damage or to the
Sorry.
person can physically hurt or
Yes. See. So why I can tell you this, because there are blast waves, all right. So these blast waves are very hazardous. So if you see like in the blast scenarios, all right. So shock waves are not just related with these aircrafts only. So if only aircraft is moving with this very high velocity, it in that scenario only there are shock waves. So when there are this detonations also, explosions also, in that case, so also these shock waves are encountered, all right. And these shock waves obviously have very detrimental effects on humans, all right. So in our lab also, like uh, one of our this colleagues is studying, trying to this absorb uh, this counter this force or energy that this when a shock wave hits a material. So this is also a particular field of study, right, where we want to minimize the this effect of shock waves when it hits some object, all right. So in this defense sector also, when like different different equipments or metals linked to defense sector, when they are in such environment where they encounter such shock waves, so it's very important to shield very sensitive things related to defense sector when there is exposure to shock waves. So shock wave is uh, like very energetic and at the same time is very hazardous, all right. It takes away, it's a lot of energy, all right. And yeah, and even there are impulsive forces linked to shock waves. So when a shock wave will hit you, there will be some impulsive force linked to that particular shock wave. So in our lab also, the studies have been done on the impulsive forces, all right. So like we here use strain gauge, all right, and accelerometer. So these are few like instruments that are used to acquire the force, the aerodynamic force that a particular object experiences when a shock wave hits this object. So studies like in our lab also, these studies have been done in the past, all right. So shock waves cannot be taken lightly, not at all. All right. how to counter these shock waves? Like, there is ongoing research in this field. Okay, so yes, compression is right. All right. So this is a very quick way of compressing particular fluid. All right, shock waves. So pressure across static pressure across a shock wave increases, right? We all know this. So from that only, you can just plainly answer this question that there is compression linked to shock waves, and later you guys will study expansion waves, right? There you'll see there's a decrease in pressure. All right. Later in the later modules, you'll come across this topic. But yes, for the time being, we will remain strict to normal shocks. Okay. All right. So characteristics of this supersonic events. Okay, this topic is from, I believe, lecture 10. Yes, it's from lecture 10 only. Right. First, this is first topic, introduction to shock waves. In this is second subheading, characteristics of supersonic events. So the question says the energy for compression of gas is derived from dash energy possessed by the right. Yes. So the compression that this shock wave does is the gas in a shock wave. Yes, is derived from the dash energy possessed by the upstream flow.
Kinetic.
Kinetic. Yes. And kinetic. Okay. So this also is correct, right? So it's the kinetic energy of this, because we are slowing down the, not we, the nature is slowing down this flow. All right. So this is being done at some cost. All right. So that cost is the kinetic energy of the upstream flow before this upstream of the shock. Okay. So from this kinetic energy only, this compression of, somehow the nature is doing compression of this shock, and eventually this leads to the flow property changes across a shock. So this is correct. All right. So now I believe I am left with two more questions, and we are left with 5 minutes only, and then we shall conclude. Okay, so the characteristics, this also is based on the same topic, the characteristics of supersonic events. So yes, supersonic, this shock wave formation leads to increase in dash energy of the flow. Yes. It's from the slides only. Lecture content. Okay, look at the options first.
Internal.
Okay, Ginny says internal. Harshit says none of the above. Okay. All right. So when there is compression, all right. So with that, there is increase in the internal energy of the flow. And by virtue of this change in the internal energy only, there is increase in the temperature, static temperature of the flow across the normal shaft, right? So the answer to this question is A option, right? So there will be increase in the internal energy of the flow as it moves across a normal shaft, right? Okay. All right. Then this, okay. Then we are at the last question of our today's session. All right. Okay. What is the behavior of total temperature across a normal shock? That this I have already mentioned. So yes. Great. Yes. Okay. I have answer from Harshit. Harshit says it should remain constant.
Increases.
Increases. Okay. Do you see this?
Total means a stagnation temperature, it will be constant.
Yes, it will be constant. That is okay. Sometimes it happens, but you should be careful, right?
Yes.
All right then. So with this only we conclude today's session. All right. So we first, as we have done in previous sessions, we have first discussed the topics related to this particular week, week 4. Then we mostly we did like this questions. Those were not all were numericals, but there were few questions were there that were numerical in nature. All right. Because in your assignment also I saw there were 2 numericals only in this present assignment. So I just focused mainly on like this conceptual questions. All right. And then we discussed the topics and then we discussed some conceptual questions and some numerical questions. And now we are at the end of our session. All right. So if somebody wants to say something, ask something, he or she may. If you want to give some feedback, that is also very, very much welcome. Otherwise, we shall end today's session. Okay then. Okay then, we shall stop here only. All right. And see you in the next session. All right. It will be on the same day, all right, of the week. that is Sunday from 3 to 5. Even also the links remains the same. And if you get, in some case, if you get delay in this announcement of this particular session, you can use the same link from the previous announcement of this tutorial session. All right, a live tutorial session, and you can join this these sessions in future. All right. Okay then, take care. Bye bye.